Obviously, welcome to Asombro's virtual teacher workshop. Our theme for today is climate change cause and effects. We're going to plan to spend the next 2 hours together doing as much interaction online, as much interaction together as we can, as well as giving you some new tools that you can take back to your students and your classrooms. Um, we are the Asombro Institute for Science Education based in Las Cruces. My name is Kelly Sayanagi. I also have with me today our education director, Gabriela Franco, and Bonnie Jean Knighton is one of our science educators. And if you're in the Las Cruces area or within about a 2 hour radius, you might see these two in your schools or in your classrooms. We'll talk about this as well, but you can always invite them to join you in your classroom. All right. Uh, Zoom etiquette. We all know the drill, but we said, please, if you're comfortable, turn on your video. It's great to speak to smiling faces rather than black boxes. Mute yourself if you're not speaking, but please do ask questions in the chat, and we'll have time for you to unmute and ask questions. But feel free at any point if you have some discussion. We really want to have discussion. If you've got a burning question, um, and you need to interrupt for it, we'll take a few of those. But we'll be watching the chat as well. Of course, take breaks if you need. If you need to turn off your camera, and grab food, stretch, walk around. We understand. We are recording today's presentation, and we'll be editing out the boring breakout room bits or the boring pieces where nothing's happening, and that there won't be many of those. We'll be editing out these and sharing in pieces so that you can see and come back to these if you want. Especially our guest speaker, Katie, who we'll get to in just a moment. So our agenda for today, here's introductions. We're going to start with a guest speaker, Dr. Katie Steele from NMSU. And then we're going to dive into the climate change education materials that Asombro has been creating and publishing, and how you access those. Today we're going to demo 4 lessons, and we'll be offering you at the end of this a kit of materials that we can mail to you for one of those lessons. And the others are very material light and or things you can print out. And so at the end, we'll do a quick wrap up. We have an evaluation form for you to fill out about us, and that form is how we know where to send a kit and if you're hoping to receive one. So don't leave without filling out that form. If for some reason you do have to drop out, I know it's a busy Wednesday afternoon, please email me and let me know how much of you are able to stay for, and I will get you that form so you have we can get your information. All right. Quick overview of Asombro for those who might not be familiar. We are a nonprofit organization based in Las Cruces. We teach about 22,000 students annually, and oh, that 5,000 is that is a typo. Should be closer to about 1 or 2,000 teachers annually through our classroom visits, field trips, teacher workshops, and our Asombro Anywhere online or physical curricula that we can mail to you. We translate science research into materials for the classroom, but everything we do is aligned to standards, specifically the Next Gen and Common Core. And we think of ourselves as a bridge between the research and K-12 community. In this case, specifically, the researchers at the Jornada Experimental Range, which is a USDA facility here in Las Cruces, and New Mexico State University, and their work in climate adaptation and what that means for us as citizens of the Southwest. In that partnership, we have been creating lessons for over the last 10 years. Asombro has been writing lessons and publishing these free for educators like you. We're now at 25 lessons. They come with educators' guides, slides, training videos, student handouts, and they're designed to be done with materials that you either hopefully have in your classroom or have easy access to. So, with that, we'll go more into those lessons later, but I want to hand it over to our guest speaker, Dr. Katie Steele. She's a college associate professor for plant and environmental sciences at New Mexico State University, and she's going to give us a little background on climate change and or on climate science, and then specifics the things she is thinking about here in the Southwest. All right.
Thank you, Kelly. I'll just get my screen shared. Okay. I think I have this set up. Okay. Can you see my screen all right? Yeah. Okay, good. So I'm going to talk today about atmospheric warming, specifically the greenhouse effect. Bit of a 101 revisit, I'm sure, for most people, and then touch upon how that influences extreme weather in the Southwest. So first of all, I wanted to have you do a check-in question. So I'm going to use the chat for this. Let me just bring my meeting controls back. Oh, there we go. Meeting controls go all over the place when you've got too many screens. Okay. What I want you to do is have a think about the greenhouse effect, and then what image comes or event comes to mind when you think greenhouse effect. Is there a picture in your mind or something that's happened? If you can type your answer in the chat, but don't press go or don't press enter until I say go. Okay, I can see people are still typing, so I'll give you a few more seconds. Okay, hopefully you've typed in something that came to mind when you hear greenhouse effect. So now press enter. Oh, I love some of these answers. Yes, the extreme weather changes that are unusual for an area like extreme flooding in Santa Fe. This is a great answer because it's kind of what I'm touching upon today. Yeah, communities of people displaced by sea level rise, something that happens. We see a lot of that in the Pacific, one of the regions which the people I work with cover in terms of climate change. Gases that trap heat. Yes, Hillary. Heavy traffic with car emissions, also a jungle. I can't quite see the connection between car emissions and a jungle, hence the laughing face, I'm sure, Nadia. But yes, traffic is definitely one of those big sources of greenhouse gases. Heat bubble over Portland, or diagram of the water being stuck in the atmosphere. Yeah, good answer, Tamara. Brown particles in the air. Well, that's like Las Cruces, like most of the first half of this year, for sure. And I love this answer. Instantly reminds me of The Simpsons, great greenhouse effect episode. And I haven't seen that, so maybe that's something I need to go and research. I love The Simpsons. Greenhouse or a car? I love this answer, Venus. So Venus is a great answer because Venus is, of course, like packed. Its atmosphere is packed full of greenhouse gases. So that's why it's really so hot. Extreme weather events, droughts, forest fires, decreases in natural forest species decrease. Yes, good answer, Camille. So these are all absolutely excellent answers, and some of the impacts you mentioned totally on target. What I'm intending to do today is talk about the greenhouse effect and then just touch upon a few of the impacts in Southwest weather. So let's keep going. Oops, click that one. So I'm going to talk about heat waves, cold events, drought, and extreme precipitation. But if at any point you think, oh, why isn't she talking about this? Or could you add a bit more about that? Please stick your hand up or place a comment in the chat. And Kelly hopefully will encourage me to stop and answer that because I might not see the chat. But yes, do feel free to jump in at any time. So let's get started with the greenhouse effect, Earth's atmosphere and the greenhouse effect. So I was trying to tell a bit of a story about, or have a bit more of a narrative about the greenhouse effect rather than just going through the science and, well, like a scientist. Like Kelly, I'm in science translation and I was much more of a scientist before I started. And I'm well aware that sometimes when scientists speak, we get a bit tangled up in the details. So do stop me again if I'm getting a bit opaque in my explanation, but I hope the story I'm going to tell today is clearer. So when we look at the atmosphere, we see that there are 5 layers in the atmosphere. And our current knowledge of Earth's atmosphere is actually the product of centuries of observations, experiments, and insights by many scientists. And I'm going to concentrate today on the troposphere and touch a bit on the stratosphere, but mostly on the troposphere. And of course, that is because the troposphere is where the greenhouse effect mostly takes place. This is where greenhouse gases absorb and re-emit infrared radiation, trapping heat. So it's the lowest layer of the atmosphere. It's the one where we live. It extends up to about 10 miles above the surface. And it's also where 80% of the atmosphere's mass exists and nearly all the water vapor. So in the troposphere, temperature falls as we go up in elevation, and it's lowest at the tropopause, which is the boundary between the troposphere and the stratosphere. Stratosphere is the opposite way round, and we see cooling as you go up in elevation. Let's see. So looking at Earth's atmosphere, and of course, most of these gases are in the troposphere. But if we look at the atmosphere as a whole, nitrogen and oxygen make up about 99% of the troposphere. If you look at the breakdown, it's nitrogen, 78%, oxygen, 21%, argon, 0.93%. And then we've got CO2 and the rest of the gases in this block diagram here. So CO2, which I'm sure you're familiar with, is one of the main greenhouse gases, but it's such a small amount compared to especially nitrogen and oxygen. So how does it have this massive effect on atmospheric warming? So we'll find out a bit more in subsequent slides here. So greenhouse gases as a whole, so these are all gases that contribute to the warming in the atmosphere. They make up less than 0.5% of the total gases in the troposphere. Carbon dioxide itself, 0.04%. Methane, well, I won't get into all these zeros, but it's a lot of zeros. Nitrous oxide, even less. And then we look at the F gases, the fluorinated gases, tiny amount as well. And then water vapor hovers between 0 and 4%, depending on where you are, and depending on altitude and weather. It's abundant close to the Earth's surface, but it's nearly absent at the top of the troposphere. So greenhouse gases, what do we mean here? So we have basically this analogy between the greenhouse that we might imagine we're growing our tomatoes in or our delicate vegetables over winter, where you've got shortwave radiation entering through glass and then being trapped within the greenhouse and warming up the greenhouse itself relative to the external atmosphere. So there are gases in the atmosphere that behave pretty much like that glass of the greenhouse. But what's actually going on behind the scenes, you've got the sun emitting shortwave radiation or sunlight, Um, and that sunlight enters our atmosphere and it warms the Earth's surface. The Earth's surface then re-emits that energy as long-wave radiation or heat. And as that's traveling back up through the atmosphere, a gas molecule may intercept it and absorb it. But there's something very specific about those gas molecules that means that they are able to absorb radiation. So we'll get into a little bit more of that in a couple of slides' time. But for a gas to trap heat within the atmosphere, it's got to absorb the radiation. Now, one thing we hear a lot about is the greenhouse effect is natural, and it sure is. If the greenhouse effect didn't happen on Earth, we would not be able to live here. The natural greenhouse effect traps enough heat from the sun to maintain a livable climate. When we compare ourselves to Mars, Mars has not got these greenhouse gases in its atmosphere. Compared to Venus, it's got a ton of greenhouse gases. So Venus, very hot. Earth is often called the Goldilocks planet because we're right in that zone that makes it possible to have life on our planet. So prior to industrialization, we have enough trapping of heat within the atmosphere that there's some stability with some variation. That with human enhanced greenhouse effect, or the enhanced greenhouse effect, we've seen burning fossil fuels emitting greenhouse gases to such an extent that we're seeing more and more heat being trapped and the atmosphere becoming increasingly warm. So I mentioned that a gas molecule has to have a particular characteristic about it for it to be able to absorb heat. I find this part really, really interesting. It's like, okay, we just accept that greenhouse gases are absorbing heat and re-emitting it. But then we've got all this oxygen and nitrogen, and they're just not absorbing heat and re-emitting it. So what's going on with that? So why greenhouse gases can absorb infrared radiation? It all comes down to their molecular structure, and their molecular structure is rather asymmetric. If we look at nitrogen and oxygen down the bottom here, you've got two identical atoms in a straight line. When these molecules vibrate, they don't create any kind of electrical imbalances. They're not jiving with the wavelengths or the frequency of the infrared radiation. So they just can't trap heat. The greenhouse gases trap heat because their molecular vibrations can absorb infrared radiation. So if you think of it like catching a wave that matches their rhythm or matches their vibration. So infrared radiation or radiation has a certain frequency. And when these gases are vibrating in a certain way, then they can catch that radiation. It's the complexity of these molecules or their lopsidedness that gives them this ability. So the more complex or lopsided they are, the better these molecules are at grabbing and holding on to the heat. So if we just take one of these as an example, so say methane, called a wobbly tripod, looks like one of those things you might stick your camera on to your phone on to take pictures. When the methane molecule moves or even stretches, it creates tiny little electrical shifts in its structure that let it grab onto the heat energy, and then that holds it in the atmosphere. Carbon dioxide is more bendy and stretchy, and nitrogen dioxide is naturally bent and lopsided. So it's these rather crooked looking vibrating molecules that are so good at trapping heat in our atmosphere. So one of the things we want to consider with these gases, there are different amounts of gases in the atmosphere, but they all have different global warming potentials. So we often talk about the relative contribution and then the global warming potential. The relative contribution to emissions, or their contribution to the actual overall greenhouse effect or warming effect, depends on three factors: the concentration in the atmosphere, so how many molecules there are, radiative efficiency, how well each molecule absorbs radiation. So we know if they're more lopsided or more complex, they're going to absorb more. And then how long the gas stays in the atmosphere. CO2 is the reference point, which is why you see that number 1 under global warming potential. When we're talking about global warming potential, this is that ability of the molecule to heat the atmosphere. So CO2 has a lower trapping ability per molecule, but it's present in huge amounts. That's 420 parts per million and rising. And it stays in the atmosphere for a long time, for centuries to millennia. So as a result, it causes about 76% of the human-caused warming. Excuse me. Methane is much stronger per molecule in terms of warming, but it's much scarcer than CO2. So its relative contribution might be only 16%, but its global warming potential is 28 compared to CO2. Then you've got nitrous oxide, very powerful. It's 265 times more potential than CO2 at driving warming, but it's extremely rare, only 0.33 parts per million. So it causes 6% of the relative contribution. And then our fluorinated gases, incredibly powerful, thousands of times CO2. They only exist in parts per trillion. Unfortunately, they do hang around for a while. They have a long lifetime. So, oops, excuse me. Our sources of greenhouse gases, well, of course, we've got natural sources. We've had life on Earth for millennia, for millions of years even. So we've got natural sources of greenhouse gases such as volcanoes, respiration from plants and animals, decomposition, the exchange between the ocean and the atmosphere, and from wildfire. But it's been over the last 150 years where we've seen this massive increase and accelerating increase more recently of greenhouse gas emissions and greenhouse concentrations in the atmosphere. So a few of you mentioned in your chat messages that vehicles and transportation is one of the main contributions of greenhouse gas emissions at about 14%. The biggest one though is heating and electricity generation, so 25%. We see agriculture and land use changes driving about 20%, industry at 17%. One thing that interests me a lot is food waste at 6.7%. And food waste is, of course, something that we can actually easily do something about in terms of like trying to mitigate changes. Other things too, of course, like how much we drive and what we drive or how we heat our houses, etc. But food waste is one of the easiest steps to take. That would be for another presentation. I'm coming back here to the how CO2 itself has changed over the last 800,000 years. And I wanted to show you this slide because it has a particular poignancy for me. I was doing field work in 1995, 1996, where I was measuring photosynthesis in plants outside, and I had to calibrate my equipment to the atmospheric level of CO2. In 1995, that was about 360 parts per million. So that's that pink dot. And I can't quite believe how much we have risen since I was doing my field work. We're now at about 420 parts per million of CO2 in the atmosphere. We have a look at this next slide. This goes into a bit more detail about carbon dioxide and temperature. So there's a long history of research surrounding how temperature is related to carbon dioxide concentrations in the atmosphere. And this goes primarily back to the work in East Antarctica, where they drew very long ice cores some which went back 800,000 years. I believe this is yeah, the Epica Dome Sea ice core, but you've got other work from Vostok as well, also in Antarctica. Then these ice cores have revealed that the pattern of CO2 in the atmosphere, and they've been able to estimate temperature changes over the period of the record. So the tiny bubbles that are trapped in ancient ice, they help preserve this snapshots of Earth's atmosphere. And it's by analyzing these bubbles that scientists have been able to reconstruct CO2 levels and temperature estimates going back 800,000 years. And we can superimpose onto this graph more recent changes in temperature. And this is what is so profound, where you see this blue line shooting up at the end towards the star. We haven't seen temperatures or CO2 concentrations rather this high over the last 800,000 years. Now, if you go back a bit further, you'll see higher CO2 levels, but that's when our continents were arranged quite differently, and we had massive changes in the geological functioning of the planet. Okay, so I'm going to move on now to the impacts of a warmer atmosphere on the extreme weather in the southwest. So one of the most obvious things to talk about is our heat waves in the southwest. So if we have a look at a rather memorable day, June 23rd, 2021, of course, we have seen hotter and longer heat waves since this particular picture. But this is a good example of how our southwest feels the heat. That if we look at the data, and this has been published in the National Climate Assessment, the 5th National Climate Assessment, we are seeing frequent and longer, or more frequent and longer heat waves. So whereas we always would have heat waves in the past, they are persevering for longer, and they are hotter. I mean, last year in Las Cruces was a good example, I think, of a very long heat wave. We've got an earlier onset of the heat season, so we're switching our ACs on, air conditioning units on sooner. And the heat season may also persist longer into fall. We're seeing record-breaking temperatures. And one of the most sobering examples of or aspects of the heat waves that we're experiencing in the southwest is that the southwest is warming faster than many other US regions, with average temperatures about 2 degrees Fahrenheit above the long-term norm. So if we look at individual cities as well, cities like Phoenix, even Albuquerque, Las Vegas, we're seeing them have a sharp rise in heat wave frequency, and that's especially since the 1960s. We actually look at the percent area of the US Southwest experiencing extremely hot daytime temperatures. So we've got area in percent in the left, and then we have got year along on the y-axis and year on the x-axis here. We have got a much higher percentage area of the Southwest experiencing heat waves since about 1995. And particularly into the 2000s. And this only goes up to 2020, so it's not even thinking about the last 4 years, which have been particularly hot. So the Southwest here is Colorado, Utah, Arizona, and New Mexico. And the threshold here for defining hot or high temperatures is the top 10%. So we're at the 90th percentile here. So these days are representing the 10% hottest in the historical record since 1910. So paradoxically, we've also got extreme cold. This doesn't happen so frequently in the Southwest, but we do get these extreme cold snaps. And paradoxically, this can be related also to global warming. And I'm going to speed through this. I realize I've been talking for about 30 minutes now, so I better make a move on. Um, so earlier this year, southern New Mexico, including down here in Las Cruces, we saw unseasonably cold mornings. And I think this happened around January or February. Someone might remind me, but we had that real cold snap and people's plumbing broke. And we saw that same thing happen in 2011, February 2011. What happened there is that your polar vortex, which is a high altitude band or strong westerly winds that rotates above the Arctic, um, usually it's trapping a pool of frigid air above the Arctic, and it keeps it isolated from us in the mid latitudes. But it doesn't often affect our winter weather, but when it does, it can be quite profound. When it's strong, it keeps that cold air bottled up. But when it's weak, it starts to spill southwards, and we see warm air moving north. And this wavy pattern on the right here, we see cold air moving south. And that is air that's coming down from the Arctic. Leads to extreme cold snaps in places that we don't usually see them. Like we heard about it in Florida, where there's not enough people down in New Mexico for the national news to report on us. But yeah, we get that too. So this is happening because of Arctic amplification, where the Arctic is warming 2 to 4 times faster than the rest of the planet. And we see that reduction in the temperature gradient between the Arctic and mid-latitudes. That weaker gradient between the Arctic and mid-latitudes causes this instability and the waviness in the vortex and also in the jet stream. And then we see those more frequent disruptions, showing that these vortex stretching events are becoming more common in fall and winter months, but also hitting us here in southern New Mexico. Got drought and extreme precipitation. Basically, we're seeing higher temperatures and less precipitation in the southwest. And if you look at this graph, just the dark red and the brown, that's not what you want to see. Dark red indicating higher temperatures between 2002 to 2021 compared to the 1901 to 1960 average. So those dark red temperatures, dark red colors, higher temperatures, and the brown colors, we're getting drier. And this slide, we're seeing declines in Western snowpack over the last century, and those are primarily driven by by warming trends leading to smaller snowpack volumes. And if we've got smaller snowpack volumes and earlier snow melt, we're seeing less water, which again has impacts down here, but it's contributing to drought, both in a hydrological sense, and we've got the meteorological drought being driven by these temperatures and reduced precipitation. Again, another paradox. Even though we are seeing less precipitation in the southwest, we are in fact seeing, because of a warmer atmosphere, there's more moisture capacity to carry moisture. And what this leads to, scientists think, is more precipitation falling in fewer precipitation events. So when storms do form with this warmer atmosphere, they have more fuel to produce short, intense bursts of precipitation, leading to flash floods, not gentle rain. So more energy in the system doesn't mean more water on the ground. It just means there's going to be more volatility. And with that, I will close there. I'm glad to see that you'll be talking about adaptations in one of the lessons, but some of the adaptations we certainly need to think about are adaptation to these flooding events, but also adaptation to heat. And then bearing in mind, we might need some adaptation to cold events too. So thanks, Kelly. Thanks all.
Thank you so much, Katie. We really appreciate you joining us today, and that was great, uh, great overview covering basics as well as taking us deeper. And will you email me your slides so I can share them out with everyone?
Yes, I will. I'll see if I can drop them in the chat now, but I'll email
Perfect.
them to you too.
Okay, great. And then We have time for like one question if anyone's got a burning question. Otherwise, we're gonna move on. But you can always share if you questions come up later, you can share them with me and I can pass them along to Katie. Laureen.
Yes, and this is something that's been bothering me here in Santa Fe. It feels like the intensity of the sun rays that are coming through to reach us on Earth has increased. I've lived here over 30 years, and it's not so much that it's more intense. And I'm wondering, is that part of things that are happening too? It's because the radiation changes. I've not heard anything about it though.
Yeah, we do have sunspot cycles, which have a minor effect on Earth's climate. I think the contribution is something like 1 to 2% compared to CO2. But the actual intensity or the flux density of radiation is not significantly higher. But what you might feel, and I remember this from doing my research in the field, um, when we have these like especially in the monsoon, when you've got these big like summer cumulus clouds that build up, in between those clouds, you've got very, very clear atmospheres. So you've got not as much water vapor and other particulates between the summer cumulus, which when you're actually measuring it, you'll see the flux density of photons actually go up quite high compared to when you've got perhaps more of a dusty atmosphere or more of an even distribution of water vapor in the atmosphere. So it's quite interesting just to go out there and measure it if you've got that ability, like on just what looks like a clear day might actually not be as clear as when you've got a cloudy day and the blue sky in between. So that's the only example I can think of off the top of my head.
That works. Thank you very much. That explains it more for me.
All right. Thank you so much, Katie. Gabriella, do you want to share your screen for the next section?
Yes, just a second.
So we're going to dive in to our lessons now. Our goal for today was to give you some lessons and some tools that really help students break down the cause and effect and see cause and effect relationships around the greenhouse effect, climate change, extreme weather, and adaptation to climate change. And so, um, we are now on to step 3 of our agenda. I want to show you real quick the materials. So next slide, please, Gabby. So as I mentioned earlier, we have 25 lessons that Asombro has written, tested with students, published for you as educators for free. They're all on our website, asombro.org/climate. And they're organized into, I think we're up to 7 modules now, 6 or 7 modules. So they're in groups, but you can do any lesson individually, or you can do them in groups as a unit. So there's a water cycle unit, there's an agricultural unit, there's a carbon cycle unit, as well as a few others. So we're gonna do a handful of those today, 4 of them to be exact. Your all the lessons and everything online have an educator guide with lots of details about background information and how to walk through the lesson is with the slides that we've created. The slides are you can download as a PowerPoint file so you can edit those, switch out if you find a newer data, new graph or anything. Um, there's student handouts, there's any printables you need as well on the website there. So asombro.org/climate, and you'll get an email from me with all of that as well later or tomorrow after this. And oh, some of them have instructional videos as well. So if it's an experiment, you can watch a demo. You can even show the students the demo and then have them follow that so you don't have to explain it. All right, next slide, Gabby. So now I'm going to pass it over to Gabriella and we'll dive into our lesson, our first lesson.
All right. Hi, everybody. Thank you for joining us this afternoon. We understand you're really, really busy, and we appreciate your time and attention. My name is Gabriella, like Kelly mentioned, and this lesson is called Insulating You, Insulating Earth. The standards that this lesson meets are on the bottom corner of the screen in case you're interested. And all of this would be on those materials that Kelly just mentioned. The educator guide would have these for you. So to start off, this is one of our oldest lessons. We've tested and piloted and taught this lesson many, many times. And so in your outline, you're going to see that the materials are showing you a metal probe and a binder clip. But we have done a new iteration of the lesson that involves a different kind of attaching the uh, thermometer probe to the student using tape instead. And it's a different kind of probe instead of a long metal meat probe. So if you have the other kinds of materials at your disposal, you're welcome to use those or switch things up. But we will be sending you, if you choose to get the Insulating You kit, we'll be sending you the kit that includes the pack of cut up Mylar for you, the timer, the tape, and the thermometer with the probe. So you would get those things, and then you'd get a class set that would allow you to make multiple groups so that you can do this, so that your class can do this and facilitate this as an experiment. So, Insulating You, Insulating Earth is an experiment that you're going to set up pretty much right at the top of the lesson. I'm going to set it up here with Bonnie, and your students are going to be given roles. They should work in groups of 4, but they can work in groups of 3 or 5, and then responsibilities can be divided or put together. So I'm going to switch so that you can see the setup, and we have taped the probe to Bonnie's thigh. The probe gets taped about mid-thigh. The probe is facing the body, and the tape doesn't go on the end of the probe, but it goes in a manner that fastens the probe so that it's close to the student's thigh and not sticking up in the air. And so the first uh, situation that we're modeling is going to be the atmosphere, and we're going to use a towel to model that. And so right now, I'm going to show you that here. So all right, can you guys see the iPad? And so this is Bonnie's lap, and she's going to put the towel
We
over
might
her
have
lap,
to
and she's going to tuck the towel
okay.
under her legs as much as possible, and then keep her knees closed. And so that is how she's set up. And she is actually playing the role of,
You might want to stop screen sharing, Gabriella, so that we can
oh, there we
see
go.
it big. Thanks.
You see that? There we go. So go ahead and tuck that under your legs. All right. Thank you, Bonnie. So, that's the way that the students will set up the model, and then you'll give them some background and some context. So I'm going to go ahead and share my screen again. I'm sorry. And so you can see the prediction that they're going to make is which situation will have the higher temperature, a towel, which is what Bonnie showed you, a towel plus a space blanket, which is this, or neither. And so they can make a prediction before they get started. Right now, Bonnie is playing the role of test subject and timer and data recorder, and I'm pretending to be the materials manager, but she's actually doing all of those things. So your students would work together. They're going to start a timer, and then they're going to record the temperature every minute for 5 minutes. So one of the students would pay attention to the timer and then let the data recorder know that it's time to record the data, and so then they'd work together so that the ball doesn't get dropped on this. And so that's what Bonnie is going to do for the next 5 minutes with just the towel on her lap. So this experiment is focusing on the greenhouse effect, and Katie's talk was perfect for this whole workshop. And she touched base on a lot of that really deep background. So this is what you would use for presenting this material to your students. So what I'm showing you are the slides that you will have access to, and then you'll just open them and use them to teach. In the educator guide, you'll have a guide for what to say on each slide, and then you have all of the worksheets and all the other materials available to you. So as Katie mentioned, greenhouse gases are these gases that trap heat in the atmosphere. Carbon dioxide, water vapor, ozone, methane, nitrous oxide, fluorinated gases are some examples of these greenhouse gases. And the atmosphere is important for life on Earth because it allows Earth to be warm enough to inhabit. And the energy that we're talking about in this situation is this electromagnetic radiation from the sun. So that's that really big arrow that says solar radiation. And so that solar radiation from the sun is coming through the atmosphere and it's being absorbed by the earth, and some of that energy is re-radiated as heat and will escape into space. So you see the thickness of the arrows is correlated with the amount of energy. So then you have these two thick arrows, and then we have some of that heat is going to be re-emitted back to Earth. And so this is the natural greenhouse effect. Now, the human enhanced greenhouse effect, the difference is that when you have more of these greenhouse gases, that means you have more re-radiated heat that's coming back to Earth. So you can see that that solar radiation comes in, is absorbed by Earth, re-radiated, and then because of the increased greenhouse gases in the atmosphere, there's less heat that escapes into space, and more of it is being re-emitted to the planet and trapped as heat. So if you think of the closest planet to the sun, it's Mercury. But is Mercury the hottest planet? No, that's Venus. And like Katie said, Venus has a really thick atmosphere that's made of a lot of carbon dioxide. So it has like a runaway greenhouse effect, and it's a good example of this situation. So humans produce more carbon dioxide than any other greenhouse gas. It's more than 75% of all the greenhouse gases that we release. So this isn't like how much carbon is in the atmosphere. This is a percent of out of all the greenhouse gases. These are the percent out of the total of just those greenhouse gases. And these gases are released by humans mostly through transportation. That's our largest source of carbon dioxide emissions in this country, followed by electricity production and industrial processes like making cement and other things like that. Now, we are providing you guys with some updated data on this, so the slides and the information that you guys will have access to will be updated from when we first wrote this lesson. So, what's the trend in this graph? It is increasing. And so this graph is showing us carbon dioxide in the atmosphere, and it's being collected at Mauna Loa Observatory. So since 1958, scientists have been collecting this data and looking at levels of carbon dioxide in the atmosphere. And Mauna Loa is a really good location for this because it's out on an island in the middle of the ocean, and it's not near a major city or place where you could discount the data because of like pollution or concentrated emissions. So the trend is that the amount of carbon dioxide in our atmosphere is increasing. And since the Industrial Revolution really has taken a high increase there. So I'm going to pause here for a moment because we are going to transition to our second trial. We're done with the towel trial, and we're going to transition to the second trial, which is a towel plus Mylar. This point is when you would start the experiment with your students. So you'd give them this background, and then this is when you'd go ahead and you'd have them start working with their materials, and they'd start their towel trial, and then they'd follow it with the Mylar trial. But in the interest of time, we've kind of doubled up here for for you guys. So on this slide, I'm showing you where the data would go that would be, can I steal your paper here, Bonnie? So this is the data. She recorded it here on the table. She calculated a difference. And so thanks for doing that. So this is where your students will record that data. They'll calculate the difference between the final temperature and their starting temperature, which is the lap temperature. Then at this point in time, or when they're done with trial one, they're gonna try to get their temperature back to that starting lap temperature, but not any cooler. So this is just a moment where the kids have to pay attention to the thermometer. A little bit of fanning it will be okay, but too much fanning it might make it cool down too much. So they'll try to get the temperature back to where it was, and then they will put the towel back over their legs as well as the Mylar. So I'm sharing on the iPad. She still has the probe with the tape to her leg. She did not remove that. And she still has the towel. And all she's done is she's brought her thermometer back to the starting lap temperature. She put the towel back on, and then she added the Mylar over. So that is the setup for trial 2. All right. So she's going to record the temperature every minute for 5 minutes with the Mylar on top of the towel, on top of her legs. So what this experiment is modeling is the natural greenhouse effect versus the human enhanced greenhouse effect, right? So we're seeing that your students are modeling something, right? The towel is modeling something, and the Mylar or the space blanket is modeling something. So what is the towel modeling? And type it in chat. What is the towel modeling? Let's see who can answer first. The atmosphere, correct, the natural greenhouse effect. So that's the atmosphere, that's the Earth's atmosphere. So what is the Mylar? What's the space blanket modeling? The enhanced, yes, the enhanced greenhouse effect, correct. So then what is modeling the Earth? The legs, exactly. So Bonnie is our world. Bonnie is the world here. She's the Earth. Your students are going to be the Earth. They're modeling the Earth, and they will love that part of the experiment. Okay. Me get back into my slides here. So that's what they're modeling. And climate, we just wanna, this is a slide that you'll share with your students. Climate is different than weather. So climate is a description of the long-term pattern of weather in a particular area. The atmosphere will influence climate. So they're related. Long-term means usually at least 30 years or more. And these conditions are averaged over a long period of time. So when we talk about climate, we're not talking about this month or this year's weather. We're talking about really, really long trends of time and data. Climate change is a phrase that refers to significant changes in measuring climate over a long period of time. Essentially, it describes all of these issues, and so it results not just in global warming or these increased global surface temperatures, it also results in precipitation patterns being different. So maybe places get less or more rain, or they get rain at a different time of year than they expect it. And then more severe storms, which we've actually seen locally in New Mexico, many examples of that. So climate change is more of an umbrella statement that captures all of these things, and it's not just global warming. or temperature related. Now, global warming is a phrase that describes the increase in global temperatures. This graph points out not only the trend that these temperatures are increasing, but it points out that kind of peak at which the Industrial Revolution started, and the graph really starts with a steep incline. Okay, so our time has elapsed for trial number 2. So Bonnie recorded her data for I'm gonna stop sharing for just a second. Bonnie recorded her data here for both trials, and she went ahead and calculated some differences here. So your students will do this, and they'll do this by group, okay?
Tell us the numbers, Gabriella. They were a little hard to read for the differences.
Yeah, so our differences for the towel, for just the towel trial, the difference is 1.2 degrees. And for the Mylar, the towel plus space blanket trial, the difference is 2.7 degrees. Okay, so all of these differences, you'll go around the room and you're gonna compile it on the board in a whole class data table. So you'll get all of those differences, and then they'll be able to come up with some conclusions. And in most cases, the trial that had a greater temperature difference is going to be the towel plus the space blanket. And as a class, which trial had a greater mean difference is usually going to be the towel plus the space blanket. Results may vary, especially if your room is very air conditioned or if kids move their legs a lot while they're doing the experiment. So just keep that in mind. But there are opportunities for talking about science, scientific methods, and there's opportunities for extension. If you have a lot of time with your students, you can run this experiment for longer than 5 minutes. Okay, so to wrap things up here, what's the relationship between these two graphs? Now, the graph on the top is showing carbon dioxide in the atmosphere and over time. The graph on the bottom shows temperature over time. And so if you just look at them at a glance, the relationship is that they're both increasing. So one is probably dependent on the other. So, all in all, our atmosphere is like a blanket. It lets us inhabit Earth and have the appropriate temperatures for that. But those greenhouse gases are pretty much acting like a second blanket, which results in temperatures that are too warm for species that are adapted to these recent historical temperatures. And this also results in big changes to weather patterns that are going to impact humans like you and I. If you have time or if you'd like to, there are some questions in this activity that can be connect to how these changes would impact other Earth systems. And this graph is a lot of fun to have a discussion, a class discussion with students about. And so you can make those modifications, and then you can choose to go over this trend of temperature change over time. With your students. So I'm just going to pause here for a moment in the interest of time. And really, this lesson talks about carbon dioxide on a global level with the greenhouse effect. But we're going to segue to thinking about carbon dioxide on a seasonal level. So I'm going to stop sharing my screen, and I'm going to pass it over to Kelly.
All right, thanks, Gabriella. Yeah, so Gabriella mentioned that was one of our oldest lessons. It's one of our absolute favorites that we've shared many times. I know a handful of you have seen that one before. Um, to one of actually our newest lesson in this series, but it still focuses on on carbon dioxide in the atmosphere. It's based off of this graph, which you saw Gabriella shared as well. And we're going to bring it to a little more local as well. So we're going to now think less about the whole greenhouse effect, but what really is happening, how is carbon moving? And so this one's called Seasonal Sawtooth Patterns in the Carbon Cycle. And it's really looking at what is this graph, what's happening in this graph. So Gabriella focused on the fact that this graph shows carbon dioxide is increasing in our atmosphere, which it absolutely is. Also, it's doing a weird zigzag sawtooth thing. We call that the sawtooth pattern. So if I zoom in on 1 year at the Mauna Loa Observatory, every year looks like this. It's just the numbers change. It shift up and down. It starts low in January, goes up till May, um, comes back down until September, and then increases again into the fall, and back up fall through spring. So, what is happening there? And that's what we're going to investigate in this lesson. Interestingly, so we use Mauna Loa as a global indicator. It's out in the middle of the ocean. It is sitting on top of a volcano, but they usually don't collect the data while the volcano is actively erupting. Um, and uh, it because it's out there, it's our global indicator. But when we look at lots of local data, we see that pattern as well. So this graph on top came from Wendover, Utah, which is northern Utah. And you see that same zigzag pattern in the increasing carbon dioxide line. And when we zoom in on 1 year, it doesn't look quite the same. We're going to look at the green line here. The red is a reference line, and I can explain it in more detail if needed, but we can basically ignore it for now. But we see again that January, February, March, April, it's higher. It looks the same as December, and then it just like the other one, it decreases to September. So we saw like a more of a zigzag in the Mauna Loa data, but here we see the same dip from like April to September, and then back up into the winter, into the fall and winter. So why is that? Well, your first step is to understand what you're seeing in the graph. So with this lesson, you start with those two graphs from Wendover, Utah, and students on their worksheet answer these questions. Where was the graph? Um, when was CO2 highest? When were CO2 levels lowest? And we have them sketch their pattern. And I used a sketchy tool on PowerPoint, and that's why this looks like such a terrible line. But you get the gist. Uh, then so now we're going to start thinking about what's happening. We talk a lot about, and we've talked a lot about how carbon dioxide gets into the atmosphere. A lot of that is from burning fossil fuels, maybe from decomposing vegetation or forest fires. There's a lot coming from soils. There's some exchange with the ocean. But to get that dip, we have to have carbon leaving the atmosphere. Something's happening April through September that carbon is leaving the atmosphere. And there's, according to this diagram, only two ways that can happen. One is this gas exchange with the ocean, which is literally gases, CO2 gas dissolving in the ocean and or being released into the atmosphere. And the other is photosynthesis, which is, of course, the process of plants taking in carbon dioxide and water and breaking it down and creating glucose and oxygen. So if you need to go over that with your students, we have the chemical equation here. I should mention this is all of our lessons are designed for they all have an ideal range somewhere in between 6th and 12th grade, and most can be adapted up and down pretty easily. This one is a pretty high school centric lesson, and while I can definitely see middle schoolers taking parts of this, you would obviously have to go into more depth. Middle schoolers might not know how to interpret this slide. So all these lessons we have tested with students, but we expect that you know your students and their abilities and how to make them really work with those students. So if you have a high school class, you could go over the chemical equations here in photosynthesis, but middle schoolers know photosynthesis as well. So I'm going to assume, based on that diagram and my knowledge of carbon dioxide and chemistry, that photosynthesis might be partly responsible for that dip. So that was a change in a certain part of the year, and I know that photosynthesis doesn't happen in all times of the year. There's going to be seasonal patterns because in March and December, plants aren't doing a lot of photosynthesis. And this is repeat photography of the same location, and I can even see how much photosynthesis is happening. Which of these photos has the most photosynthesis occurring in it is going to be the greenest photo. So phenology is the study of seasonal patterns in living things. So we're bringing in phenology here. It could be the study of when plants green up, when they lose their leaves, when they bloom. It can be the study of migration. It covers a lot of things. And in this case, we're looking at those seasonal cycles in plants and photosynthesis, which is monitored by this really fun tool. There's a network called the PhenoCam network of scientists all around the world who set up these cameras. They take daily pictures. They're like security cameras. They're attached in place. They're connected to the web. So it takes a picture, it sends it to the database. A computer analyzes the pixels of that picture for how many green pixels are there and how green are those pixels, and creates graphs like this of how green is this picture throughout time. And so this is January of 2021, 2022. So this is 4 years of, or sorry, January 2021, July 21, January 2022, July 2022. So we're looking at several years of data here. And this is a cool tool that we're going to look at today. And as I said, they're literally measuring the greenness of the pixels. So each pixel is a combination of RGB colors, right? And the greener the plant, the more chlorophyll is present, increasing its ability for photosynthesis. So in a few minutes, I'm going to send you to this site, the PhenoCam website, which is phenocam.nau.edu. You're going to click map here in the top corner, and I will give you all these instructions again, don't worry. I would click this button to add in the streets layer, which gives you the state boundaries and the highways and the cities. And then any of these green dots is a phenocam. And if you click on a dot, you'll see a little tile like this pop up. You'll click on that picture and it'll take you to that PhenoCam's page. So here is the latest photo from that PhenoCam. I can browse the images. I can look at every picture it's taken, and it takes like one every half hour or something. There's many pictures per day that it analyzes. And I can also look at, it's called the ROI time series, and that is this graph, this data of how green and what is the seasonal patterns. And you'll notice, obviously, there's pretty up and down patterns because it follows an annual cycle. The gray bars are no data points. So sometimes there'll be a big gray patch where the camera wasn't working for a while. And there's just no data from there. And sometimes it's just a couple instances where the data was missing, and that's not a big deal. So we're going to compare this data to that graph we were looking at from Wendover. So we need to get this to 1 year of data. And these sliders along the bottom of the graph help you get to a start and end point. So using the slider on the left, we got to January of 2023, and using the slider on the right, we pulled it in towards January of 2024, and you'll see here I got to a point where, yeah, that's a 1 year of data. I scooch them in. Now I have all my years, all my months there. And note the number there is the year, not the date of the month. So January 2021. So you can move the sliders to adjust the date on your graph and set it up so you have 1 year. So you have January to December, or January to January of the next year. And you're going to compare that data to the data we looked at from Utah. So your choice is your options are in this time to just find any graph and any phenocam you're interested in and find that pattern. You can find one near Utah, somewhere in Utah, northern Utah, to match up to that local data. You also, as the teacher preparing for this lesson, would have the option to find some CO2 data from closer to home. This is a NOAA website, and I'll give you the link for that in a moment as well. And that's in the lesson that has carbon dioxide monitors. That's where the Utah data came from. Unfortunately, at this moment, they don't have any monitors in New Mexico, any monitoring stations in New Mexico. So we have to go to neighboring states. But you can use this and click this carbon cycle, click on a dot, red dots are active in this one. Click on carbon cycle gases and it'll let you see like a time series or a seasonal pattern. And you can do that as well. But what I'm gonna ask from you all right now is I'm gonna give you time. We're gonna drop these links in the chat. So you'll have a link to the PhenoCam website, a link to that NOAA website, and you'll have this worksheet as well. And here I'll leave this slide up so you can look at you can see the instructions on this computer or on your computer instructions here, which assumes that you are letting your students do this work on their computer. If you have younger students or you just don't have the time, not everyone has a computer, you can pull up these graphs either as a class or you just give them the graph and analyze the data together. But I want you to go explore the PhenoCam website and fill out or find a graph that you could sketch for the bottom part of this graph. So I'm going to stop. I'm going to give you about 10 minutes to do that. And then I'm going to call you back. And my call will be a bird call. Caw-caw, caw-caw. And then we'll all come back together and talk about what we found. So, hopefully in your investigating, you were able to see both some patterns in the phenocam data, but also whether you were looking visually at the photos or um, at the graphs, I guess are visual as well, numerically at the graphs. But were you able to find something? Give me a thumbs up in the chat or on your screen if you found something that kind of matched this pattern I've got on the bottom part of my screen here, where we're low in January through maybe May, starts to creep up, and then around September, October, it turns back down. All right, we're able to find something like that. So, we are identifying correlations here. We don't have the data to prove causation, but I am seeing a correlation that I've got my top graph was like kind of flat and then had this big dip and went back up, and my bottom graph is kind of flat and then that has this big bump and goes back down. So on the back side of our worksheet, we've got question 5 is comparing our two graphs when our GCC, which I don't think I went into, it's our greenness unit. It stands for green chromatic, something that was on the last slide. Green chromatic, I've lost it. Sorry. I'll find it. Green chromatic coordinate, sorry, it's on the worksheet. When our greenness is high, CO2 levels are low. And vice versa, when our greenness is low, our CO2 levels are high. So we can build a correlation there between plants doing photosynthesis and carbon dioxide coming out of the atmosphere. And this is an example then this feeds into a feedback loop, which I know is a hard topic to teach because they're hard to find really concrete examples. So with what we've been looking at, we have our increasing CO2 in the atmosphere leads to increasing temperatures. That's what we saw in our last activity with our laps and our blankets and our mylar blankets. That leads to increasing evapotranspiration, which is the combination of transpiration, plants using water, and evaporation, water evaporating, all of that within an ecosystem. So that means there's less water available to our plants, which means our plants are doing good or bad? Bad. So that means they're going to photosynthesize less. If plants are photosynthesizing less, are they pulling that carbon dioxide out of the atmosphere? No, which means if they're not doing that as fast, it's going up, which means we're increasing our temperature, increasing our evapotranspiration, and we've created this positive feedback loop. Note positive feedback loop means in something that is destabilizing. It doesn't have a positive effect necessarily. It's just a destabilizing. It's creating more and more of the situation. There are some discussion questions like, okay, what does a wildfire mean then for local CO2 data? Or what if we had a city tree planting campaign and we planted 100 trees? So you can think about, again, locally, this global phenomenon, but we can see it in the local data as well as the global. And then there's also data from like the Arctic Circle. So you can really start to think about crazy, cool things that are happening up there, but I'm going to leave that because we're already a little behind. So, with that, I'm going to pass it back to Gabriella. I'll let her share her screen instead. And now you're going to play a game.
Can you hear me? I think you can hear me now. Share. Share. We're almost there, guys. We're almost there. This next lesson is called Streams and Steams, and it focuses on these effects that climate change will cause, and it focuses on the water cycle. So this isn't something we're sending you, but it's really easy for you to get a hold of these materials. You'll have access to all of everything like we said before, including the game board. If you wanted to print it in grayscale, you can print it on an 8.5 by 11. You print the other half on a different piece of paper, and then you tape them together and you can make your game board. If you're fancy, you can laminate it if you want to, if you have that available to you. I have a game board here that's put together and laminated. And then you can use dice and like little chips. You can use coins. Anything for the player pieces can be like almost anything, like lint from your pocket is fine. And then die would be like the one thing you might need to get a hold of. So this is called Streams and Steam. And basically, it's based on chutes and ladders. Okay. Now we've learned that not all kids actually know what chutes and ladders are. So you might need to give them some context, but it's based on chutes and ladders. And it's a special board that's based on the water cycle. Everybody, all the players, it's meant for up to 4 players. All players would start on the start square, and then they'd all roll a dice at the beginning to see who gets the highest roll, and then that person would go first, and then you just go in order from there. And all you're doing is moving your player piece the same number of chips, same number of places that you have rolled. So very straightforward. Now here's where the quirkiness comes in. That's like chutes and ladders. So the chutes are going to be the streams, and so if a player lands at the top of a stream, then they raft down the stream, and they go in the direction of the arrows, which you can see here. And so my piece moved from 17 down over here to square number 5. And then they'll stay there. And then if a player lands at the bottom of a column of steam, that's your ladder. And so those players would follow the arrows and they would end up moving up. So those are the rules. And then other than those rules, no text on a square, like no problem, no action required. You just wait for your next turn. More than one player can be on a space at the same time. That's fine. And in order to win, all you have to do is pass finish. You don't have to land exactly on finish, like with the number, like a dice roll. So those are the rules. So what we're gonna do is I'm gonna have you guys play for just a couple of minutes. You're just gonna get a taste of it. And just so that way you know what we're talking about, because after they play, you're gonna connect this back to climate change and the water cycle. So we'll ignore action types right now, but we'll focus on causes and effects. So if you have a little scrap piece of paper, grab it. If you have like you're on a computer and you have like a Word document or a notepad you can open, just go ahead and open that now. And we're gonna put you guys into breakout rooms in small groups so that you can play virtually just for a few minutes. And as you play, you're gonna look at causes and effects and write them down for your turn. So if I were looking at this part of the board where square 3 says increased evaporation, that's my cause. And then I follow the steam clouds and I land on square 9 that says more severe drought in some areas. That's my effect. I'm just copying those down at the tops and bottoms of the streams and the steam. So give me just a moment. You recorded some causes and effects. If you'd like to, you can go ahead and just throw those in chat. But I'm just going to go over what you would do with these causes and effects. So your students would fill out this table that's on a handout, and they'd come together and they'd try to agree on action types. So A is water conservation, use methods to decrease water. My Zoom tools are in the way. Use. B, mitigating climate change. Use methods to reduce greenhouse gas emissions. And C, risk management planning. Follow procedures to avoid or minimize the impact of climate change. And so for the example that we have, increased evaporation is going to cause more severe drought in some areas. Now, we can actually do all three of these action types to help mitigate the effects of increased evaporation. So you're allowed to list more than one action type per cause and effect, or your students are allowed to do that. And then, so they'd fill this out as a team, and they don't have to write causes and effects over and over if more than one person, or if they were landed on multiple times. So if someone else landed on increased evaporation and the same effect, then we don't have to write that over again. But we'll compile our list, and then we'll continue to, this is a sample answer. So this is a really, really long, and you get this answer key in the files you have access to. So then you lead a conversation with students on choosing one of those effects from before and explaining how that change to the water cycle would affect humans and people. So more severe drought in some areas will affect crops and livestock for people. More water in the atmosphere will lead to increased precipitation, etc., etc. These are just some sample answers. Your students will come up with their own answers. So and then this is how the table looks once it's your students fill in those causes, effects, and those actions. So in the interest of time, I'm going to go ahead and pause here and segue to Bonnie. I'll stop sharing. And this activity helps students think about mitigation and adaptation. So this is a great segue into our next lesson.
Unmute, Bonnie. You're still muted. We can see your screen now. There you go.
Okay, now you can hear me. All right. So we're gonna zoom through this one because I want to give you guys time to talk with each other again in a breakout room. But now that we've talked kind of what is climate change? Why is it happening? What are the trends? What are the effects? We're gonna end by talking about mitigation. Go ahead and go to the next one. So nowadays we're talking a lot more about adaptation because we are seeing the effects of climate change, and there is ways that we can adjust to the climate change that's occurred. But mitigation is still a really important key part, and being able to have these conversations with your students about reducing climate change and its impacts, not just how do we adjust to this, but how can we reduce our effect, our impact on climate change is important. Next slide. So we've put together a lesson that helps to navigate that conversation and give your students a chance to really build the skill set of evaluating data. So this lesson is based around this this research. Thank you. This research that was done by Wines and Nicholas in 2017. And what they did was they didn't just look at, because we talk to students a lot about what can we do to mitigate the climate change, but we don't talk about, well, what is that impact when we do this mitigation over that mitigation? So they looked at the actual impacts of different mitigation options, strategies, and this is kind of what it's based off of. So we've given you these mitigation strategy sheets that have kind of data around that, and that, why is it not showing? Are you guys seeing the circles? No.
No.
Okay, there we go. It's delayed, I think. Okay, so yeah, so these are the 5 that we have strategy sheets for you. And these strategy sheets, they kind of go over like the different challenges that there is, as well as the ways that we could make it happen. So there are challenges to each of these, especially have one fewer child is a big impact. But you know, there may be different cultural aspects or other issues, economically speaking, that might impact the decision to make that choice. So it's really having a conversation around those tactics and the pros and cons. And just to keep in mind, go ahead and go forward. So what we're covering here is how to evaluate the data. So we're going to do an example really quick, solar energy. So we all know about solar energy. It is a renewable source. It could impact the effects of climate change by reducing CO2 by 0.5 petagrams is what that's called. So it's like 1 billion metric tons, essentially. It's a lot of CO2 in the air. But it takes a lot of space, it takes a lot of money. And so some of those challenges will impact our decisions, and it will impact what we need to think about in order to make it happen. So your sheets will go over the challenges and what can make this happen. Go ahead and go to the next slide. So with solar energy, of course, we know, go ahead and click forward, that cost is a big problem. And the costs are reducing every year. They've significantly reduced, but it is something that is still an issue, as well as space, because it takes a lot of space for solar panels to be able to, and it needs to be in a sunny location, right? So it's going to be a big challenge. So let's look at the stakeholder cards really quick. So in your lesson, you will get these stakeholder cards, and this is just a way to enhance your conversation about this first example of the solar panels, because it helps the students think outside of themselves and be thinking about this challenge in a different way. So a coal miner is definitely going to be thinking about the impacts of putting in solar panels in their community in a very different way than a doctor would, right? So just having them think through like, well, why would a water quality expert think about the pros and cons? What would those pros and cons be? And then, so that's for the solar panel. But as a group, you can go over the Earth solar energy, and you can talk about the different ways that they can mitigate. So this is a mini poster that you're going to fill out with your students. And then when you separate into your individual mitigation strategies, there, as a group, they will fill out their own. But it's just, it's going over who's going to be involved. So these are our stakeholders, and what is the pro or con for them? What would they be for or against? Where will this happen? So again, with solar energy, you're thinking this is going to cost a lot. So which states or countries could afford to do it? What are the biggest challenges to implementing this strategy? So that's kind of the biggest challenge that they need to overcome. But then you're going to also have them looking at their arguments for or and against. So what pros are there, multiple pros, what multiple cons are there? And then the very last one, explain how you will implement this mitigation strategy. This is that critical thinking part where they have to think through the problem solving process of, okay, these are our biggest challenges. How can we take care of those so that we could make this mitigation strategy work? So it's just a discussion base, and we're going to give you guys 5 minutes to look at this together. All right, welcome back. So obviously we would probably want to, with our students, have a group discussion again about like their findings. They could present their posters, but we don't have time for that right now. So we're gonna give you just a few more details, how you can get that kit of supplies and other information, and then we will let you guys go on your day. So Kelly, you want to take over? You're muted.
Okay. Thank you. Yes, so apologize for the speedy pace at which we put you in and out of breakout rooms in the last bit here. We wanted to give you a taste of these lessons so that you could feel like inspired or prepared or to go look them up. And that maybe tomorrow, if you need something to do, y'all can play some streams and streams or something. But just a reminder that those were 4 of 25 lessons. There's wildfire lessons, there's carbon cycle, there's all sorts of agriculture lessons, that these are meant to be um, Southwest based lessons, Southwest examples that you can bring to your students to really help them make those connections for this really big global issue and break it down into little pieces. So whether you're teaching physics or biology or earth sciences or like middle school or high school, there's something in here that really will connect to your standards and things you're doing. And we are happy to help you find those. If you are looking and you want specific topics, please let us know. Now that you've been with us in a workshop, we want to stay in touch. We want to be your friends, and please don't drop out of contact with us. Thanks for watching. Please feel free to reach out with any questions and make sure to visit asombro.org/climate for all our climate change resources. If you live within a 2-hour drive of Las Cruces, we would love to come visit your classroom. You can find all our K-12 programs at asombro.org. Or come visit us at the Chihuahuan Desert Nature Park just north of Las Cruces.